And then we're going to go over some regression modeling. I'm going to talk a little bit about some different types of regression, but then we're going to focus mostly on PLS. And then we'll do like a quick summary. So some history behind doing multivariate data analysis. Originally, the scientific approach typically used only one variable at a time. These are univariate methods. This is mainly due to the fact that there weren't very many measurements available and there was limited spectral resolution, so you could get away with that. In 1975, though, we started having much better instruments that had higher resolution, and you wound up with many variables in your data points. And so chemometrics came along. So we had cheap measurements, expensive instruments, and then we had to develop new methods in order to analyze the large data that we have. So as we all know, our world is actually very multivariate in general. If you think about the weather, there's lots of factors that go into the weather, such as wind, air pressure, temperature, dew point. And to measure those different types of things, we have many different sensors, an anemometer, barometer, thermometer, and we use these things together to predict the weather. So typically in a process, you would have a lot of univariate control charts. You would see something like this. You're looking at temperature and pH in a system. And if you look at your statistical limits, there's nothing stands out. Nothing will cause any alarms in this case. However, temperature and pH in this particular case are related to each other. And if you plot them against each other, you see very quickly that in a multivariate space, there actually is an outlier. So something is wrong here. It doesn't follow the general trend with when you plot the temperature and the pH against each other. So sometimes you can only detect some faults in this way. And that's why we want to apply multivariate data analysis. And we also sometimes need to make indirect observations. So if you're taking the temperature of a furnace, for example, you can't really put a thermometer in there because it will explode. So what we do is you take an indirect measurement with an infrared emission spectrometer, and then you apply multivariate data analysis, and you can calculate what the temperature in that furnace is. There's lots of different types of multivariate data that we can look at, and we'll look at two different types today. We have sensory data, so this description by panels or instruments often works with customer preference. We also have spectral and image data, so near-infrared, fluorescence, MRIs. And then you also have chemical data, your raw material, your process variables, and your end quality measurements. And using multivariate data analysis will allow us to get information out of all these different types of data. Spectroscopic methods are very good for chemical nature and composition of different sample types, and it can provide physical and chemical characteristics of the samples at the same time. They're often highly multivariate and require these chemometrics to pull out the information that you really want. So data analysis in practice. 70% of what you're going to do with your data is important that you know what you're doing. It's your application knowledge, your common sense, because you are the expert in your data, and you're the only one who can really make sense out of it. So there are about 10% is the statistics and mathematics, and that's what the unscrambler provides for you. So we make the tools to apply the statistics and the mathematics simple so that you then can apply your application knowledge and common sense to pull out the information from the data after using these tools. So what is regression modeling? So you have a problem here. We have some samples that we need to know their weight, but we don't happen to have a scale. So you might have this idea that we know that weight can be related to a spring. So if you take an experiment and you design it and you take different weights, known weights, and measure how far the spring is expanding, then you can create a regression model like this, and from the equation you can determine what an unknown weight is. So there's 3 steps. You have your experiment, you have your modeling, and then your prediction. When we collect data on a system, we usually plot the variables together. And if they lie on a straight line, we say there's a linear relationship. This is what we like to do in regression modeling. We want a linear relationship. We use least squares to obtain a predictive model so that you can use your model later to predict new samples and have some confidence that those values are accurate. You can also use the model to estimate future samples based on the quality of the method developed. So let's just take a quick look at your traditional linear regression. You plot x and y together, you fit a straight line, and then you use your matrix algebra to determine the model parameters. In a univariate regression, you've got your y-intercept and your slope, plus some error. And the aim of the least squares is to minimize this error term. Now this holds true in a multivariate space. Multiple linear regression is just a sum of univariate regressions. So you have multiple x variables, and so you'll still have your y-intercept, and you'll have a slope connected with each individual value that you are looking at, and then your error. The problem is with this is when your x variables are correlated to each other, it can become unstable. And also this only works when you have a small number of variables, which is not the case, especially in spectroscopy situations. There's also principal component regression, and what that does is it takes your data and looks at your x space and looks at the variability of those data and plots it in the principal component space. And then it looks at building a regression through that space according to y. So it's you still have your y-intercept and your slope term, but now instead of your raw x values, you are looking at your PC scores. Now partial least squares, the difference with this then is you basically do 2 PCAs. You do a PCA of your x variables, your dependent variables, and your PCA on the y space, so your independent variables. This is to minimize the covariance between x and y, and that's how it's different from PCR. Principal components regression only does the principal components on x, where partial least squares does it for both x and y space, and then you plot it in a new space. So you have the scores in y and the scores in x. So some common statistics we want to look at when evaluating our regressions is your root mean squares error. Now these describe how far away from the line, or a prediction line, that the values are. So we have different values for this. There's a root mean square area of calibration. That's going to be your original model. So that tells you how well the calibration predicts itself. You have a root mean square error of cross-validation. So that would be when you take some of your samples out, depending on how you want to do this, and make your calibration, predict them back in, and how well they predict. And that gives you your cross-validation. And then you have a root mean square error of prediction, which shows the performance on new data that were not used in your original calibration set. That is the best way to really test your regression model, is to have 2 separate sets of data, one that you use for your calibration and then known samples to use for your prediction. We also look at the bias. If there's a systematic deviation from the fitted line, then that's what this is. It shows that a majority of the samples are predicting high, for example. That would be a positive bias. This is very different than intercept or offset. And then we also look at the slope. Ideally, for a linear model, you want a slope of 1. So the intercept is the point at which the fitted line crosses the y-axis. It doesn't necessarily have to pass through 0, just like in a univariate linear regression. And then another big thing we look at is R squared, and this is the correlation coefficient. That tells you how straight the line is, how well the data fits to those lines. And in the unscrambler, you can look at both, all of these statistics for both the calibration and the cross-validation. So the R-squared value is applied to all prediction reference plots. This is a measure of how much variance is captured by the specific number of components or factors. The closer the R-squared is, the Pearson R-squared is to the R-squared, the more reliable the model, assuming that you're not using an excessive amount of factors. We already talked about some of this terminology. These are the things that we tend to look at, the RMSECs, RMSCVs, and SEPs. So let's look at a quick example. Log into the unscrambler here. So what I'm looking at here is some data on paper and if there is ink print through. And we have a number of different variables that we're looking at. Weight, ink, brightness, scatter, opacity. It's very hard to look at this and see if you can predict the print through. So one thing we want to do first is we want to look at our variables. This is always a good thing to look at your data to get an idea of what you have. So I'm going to look at the descriptive statistics on my process data for all. And these are going to be our box plots. So these are going to show your median, your quartiles, and then the full range. So each section of this is a quartile. So this is 25% of the data falls within here, the next 25% falls in here, and so on. And what we can see from this right away is that all of these variables are on different scales and have different ranges. This tells us that we're going to need to scale our data before we do any analysis, or else everything's going to be biased by these density variables and the permeability. Because they have very high values, they are going to affect the regression more so than these other ones that have very small values. So if we go back in here, we can go to tasks, analyze, partially squared, and I'm going to use the process data to predict quality on my training set. Now here is where we make the weights. You need to select all of them, and we're going to do a very standard weighting, which is just the 1 over the standard deviation. Make sure to click Update, and you will see here that the weights have changed. You can also do these individually if there's something that you don't want to weight differently. So you can always change those all individually. But in this case, we want them all the same. We're going to go ahead and weight the Y variable as well. And then we want to check our validation. So there's a number of different ways you can do cross-validation. There's symptomatic, where it looks at every third sample, or you can do like batch-wise systematic. You can come up with your own custom cross-validation if you want to, full and random. We're going to go with random, and it's going to pull out, we're going to do 20 segments, which pulls out 5% of the data, and then runs your calibration, predicts those 5 samples back in, and it goes through and has until every single data point has been left out and predicted back in. We say OK. And now we have our model. So let's look at our loadings first. I'm going to turn on our labels. And what we can see is that this is our print through, this is our Y variable, and these are all of our X variables. And just as in the PC loadings plots, we can say how things are correlated to each other. So you can see that print through is far over on factor 1, and opacity is across from it. So that means that opacity of the paper is indirectly or anti-correlated with the print through. So the more opaque something is, the less print through there is. The less opaque it is, the more print through it is. That makes sense. You're also anti-correlated to weight, filter, and you're slightly correlated with brightness and ground wood. Another thing we can look at is our correlations loadings. And this shows us how much of these variables are being used in each factor. So this inner circle is 50% and the outer circle is 100%. So anything that lies between those two circles is usually is contributing significantly to those factors. So in factor 1, you're basically looking at opacity and scatter are the highest ones. And then in factor 2, you're looking at roughness. And print through is very high on factor 1. So if we look then at our prediction model, this is actually fairly good. We have a reasonable R squared. Question is, how good is good? It depends on your particular situation. In this case, 85% is not too bad. If you look at your RMSE and you compare it to your reference, you've got about a like a 5% error or so, which really isn't that bad, and a decent slope. If you look at your explained variance here, you can see that it's explaining a lot in the first factor. As we saw, print through is related highly with the first factor. And then the second factor gets us a little bit more data. You wouldn't want to go any past 2 in this case because there is a plateau. So adding factors 3 or 4 doesn't really add any more information to you. One thing we can look at for that is if we look at your XY relation outliers, this will help you choose some of your number of factors that you want to consider. And you can see here that there's a fairly linear direction of this data in factor 1. It's starting to degrade in factors 2. And then factor 3 and 4, it just looks like a scatter plot. So there is no real relation to Y in factors 3 and 4. So what I did too is I did an uncertainty test. I forgot to point that out. But what that does is it helps show what the important factors are. And we have that. The important variables. The uncertainty looks at how the variables change in relation to your Y value. And if the variability crosses 0, it shows that there is no real relation, so they are not important factors. And so we can see here that opacity has a strong negative correlation to print through, and so does weight and scatter. And brightness and roughness, permeability, they don't have a large influence on that. Now what we can do is we can recalculate, or if we go back here. We can see if we look here, factor 1, it explains 18% of our X data, and that explains 81% of our Y data. So that's telling us here that we have a lot of X data that is not important, and which is why you might want to do some variable reduction here. And we can do that by doing recalculate with unmarked downweighted. Now we can see that our RMSEs go down a little bit. So we have a slightly better prediction with this model. But we're only using those few factors this time. And now we have 30% of the data is explaining 83% of the Y data. And if we look at the correlations plots again, we can interpret where these fall into space. Again, the opacity is a key factor, anti-correlated with the print through and the scatter and the weight, and a little bit of the roughness and the permeability. But you could actually probably get away with a one-factor model here because you still have a very good RMSE and R-squared with this particular data. So we'll go back to our slides. So when you're interpreting a regression model, there's 5 steps. You want to look at how many components do you want to take into account. You look at that using your explained variance plot. The number of components in the model is characterized the structure of the data. Fewer PCs is a more parsimonious model, which means later it should be more robust. You want to look at the scores plot. You see how well the data are distributed. Are they all clumped together? Is there any pattern in them? You can see groupings and similarities and differences there. You also want to look at your loadings. Your X and Y loadings is where you understand the correlations between your independent variables and your response variables. And that's how you interpret what variables are describing your Y, what you're trying to predict. You look at your predicted versus your reference. It's a good way to check the quality of a regression model. Again, this is where your RMSEs are to see, and your slopes and R-squared. You want to look at your B coefficients. Those are the regression coefficients in PLSR models. It provides a summary of your X and Y relationships. It's useful in your variable selection, and that's what I showed you. So the B coefficients show the relative importance of each X variable, and it shows how they're used in the equation. And the stability of these coefficients is what helps you see what your important variables are. So how do you choose the number of components? As you increase the number of components, by definition, your calibration variance will decrease, your residual variance, and you will have explained more and more of your variance. Now, with your validation, what's going to happen is you want it to follow the same curve as your calibration. And as soon as it starts diverging, that means you've gotten to the point where you are modeling noise. And you don't want to do that because that makes your model less robust and does not predict as well. So once it starts predicting worse, then that's when you're going to stop. So you have to be careful. You don't want to use too few components because then you're going to underpredict and it doesn't describe all of your data well and you'll have poor prediction. You also can get in the place of where you're overfitting. A model with too many components will describe the noise in addition to the structured variation in data, and that also gives you poor prediction performance. So you really have to play around so you get your sweet spot. And that sweet spot is different depending on what your data is and what information you were trying to get out. So if we look at our scores plot, again, you can see sample patterns. In this case, you can see different types of fish are coming out in your scores plot on your PCs. If we have like with the print through, let's see if we can go back to that. We can do sample grouping and group it based on quality, create row sets. And as you can see, you start with things with higher opacity here, have less print through, and as we get over here, these are more print through. So that would make sense. So you would expect to see this in this case. So again, this helps you group your data and visualize what differences are there. Again, you're going to look at your loadings and your correlation loadings. This is where you actually interpret your model and look at what things are correlated. In this case, your EPA variable is strongly correlated with the diet of the salmon. And here, the BMI and sex are highly correlated to each other, but they are anti-correlated with the diet of salmon. The predicted versus reference plot shows how close the fitted responses are to the observed ones. And that's where you get your regression line. And you look at your summary statistics, your slope, your offset, R-squared, RMSEs, and so on. So your error measures, the equations, they are your residuals. The residuals are, it takes your original Y data and then subtracts the predicted Y data to show you how close it is, how much error you have in those two things. Your variance, you take the difference of those and square them over the whole place, divide it by n, and then you take the square root of that, and that's how you calculate your root mean square errors. So the B coefficients, again, the uncertainty test provides an automatic detection of significant variables. Again, make sure that you look at these yourself and that they make sense. If you cannot interpret them, then that's a bad thing. You need to look at it a little bit more deeply. It requires cross-validation, so you have to do a cross-validation. And in the unscrambler, we always do a validation. If it's cross-validation or a test set validation, every model that you build will have a validation. And it automatically marks your variables in the plots. And you can turn those on and off depending on if you want to use that or not. So this uncertainty test, it helps you draw your conclusions on the robustness of the model and the importance of those variables. And this is the equation for how we model those. You've got your B coefficients with your main model and your submodel, and it's the error between those divided by the number of segments that you have. So let's look at another regression example. Close this one. Open. So in this data set, we are looking at some fuel samples and trying to predict what the octane level is based on near-infrared spectroscopy. We have a couple of different rows here. So we've got some that have additives in them, some that don't. And then we've got high, medium, and low ranges. So first thing I always do when I get spectral data especially is I plot it to take a look at it to see what there is. So we're going to plot our NIR spectral data and make sure that we click sample here. We can see we have a fairly good consistent spectrum, but you see that there are a couple here that have a very different structure up here. If we go to sample grouping, we can look at additives, create row sets, and we see that those are the ones with the additive. Now this additive is alcohol, and this is where you find your OH bands, so this makes sense that it would have a different structure in that area. But all your straight chain and broken branch chain hydrocarbons are down here. They're not affected as much by the additive. So let's just do a regression on this now. Training set, spectra, and octane. In this case, in spectral data, we don't really weight variables because everything's on the same scale, and the variability that we see on those as they're changing actually has real meaning. To Brandon? Okay. So what we have here, first thing we want to look at is the explained variance. And you see here in factor 1, it drops down, the prediction value drops down very significantly. But then it comes back up in factor 2 and factor 3. So this sometimes is an indication that you may have some outliers or extreme samples in your data, and you want to take a look at that. But basically what it's showing is that factor 1 does not explain something, but then by factor 2 it actually pulls it in. So we might want to go then look at our loadings. Because we have spectral data here, we want to look at this in a line. And as we see, factor 1 has this OH peak that we saw with the additives, so that makes sense. So, and then factor 2 is the one that includes your hydrocarbons. You can see this in your scores plot quite easily as well. We'll go ahead and color these based on additive. And we see, of course, that our two samples here with additive are showing up further away on PC1 than the other ones are. And so this is another way that you can notice if there are outliers. If you see that a bunch of the data is trying to line up along PC or factor 2, then that tells you might have some extreme samples that the first factor is separating those two things. So you have to make a decision on whether you want to include those extreme samples or not. Now what we see here is that there's still a fairly good prediction. We've got like a less than 1% error if you look at 0.3 error out of, say, 90 in the middle here, and a very good R-squared. It's over 95%. Now, what we're going to do now is I'm going to show you how you can remove those outliers if you want to. We can just click, we mark on them here. And one of the great things about the unscrambler is when you mark them in one figure, they are also marked in the other one. So you can see where those particular samples lie. We're going to go to recalculate without marked. And now we see a much cleaner explained variance plot. The cross-validation follows almost perfectly with your calibration. We have very similar RMSEs and the R-squared. Now if we look in here, we can do some sample grouping again based on your type. So that's those low, medium, highs. And we can see that there is some grouping that is happening in your first two factors. Now this means that maybe if you want to predict even more accurately, you might wind up doing a classification first. So you could classify these are low samples and then build a PLS model just based on those, and then medium and high if you would like to. So now what we want to do, like I said, is we want to see how this works for prediction. So task predict our regression model. We'll use PLS here. Include our Y reference using our test set, NAR spectra and octane. Okay. And this shows what our predictive value is with their assumed deviation. So it looks at how accurate this prediction is according to the model, like how close these data points are to the original data points in the calibration model. And when you see the very small box plot here, that means that these samples are very similar to the ones that were in the calibration. And if there's a large deviation here, that means that there is a big difference in those. But it still looks like they predict fairly well. We can also look at your predicted versus reference. And this is where you can get your R squared and your RMSCPs. And you can put your target line. So that would be a 1-to-1. And this is your regression line. So you have a pretty good accuracy of predicting, even though you had those outliers. And if we look at, back in here, our predicted with deviation, we see that it is these last four. If we go back and look at our original data and you look at the last four here, you see that those are the ones with the additive in them. Now, if we look again, you can predict based on the one that included the additives. And that actually predicts them all quite well. And now you've included that those extreme samples that had the additive in it. So you just have to decide for your particular problem how you want to handle those extreme samples. I'm just going to go through another quick example here on a work environment. They looked at, in a company, looked at 34 different departments and asked their people questions and then related that to their overall job satisfaction. So these are all your different departments, and as you can see, in your first PC, you're explaining about 50% of your variance, and then you start losing your prediction value after about factor 2. So you would not want to use more than 2 factors from here. And if we interpret this, your satisfaction is very correlated to whether they enjoy their work, they get acknowledgement for their work, they get to make their own decisions, and then it's anti-correlated to repetitive work and conflicting feedback and disrespect, which makes sense. And so you can go in here, you can see, so Department 23 here must get a lot of conflicting feedback and disrespect and maybe some repetitive work, where Department 30 and 33, they get acknowledgement, they have enjoyment. Department 1 down here, since it's down here on PC2, probably has too high expectations and not enough time to complete it. So this gives you a way to look at the space that your variables are in and understand what's going on. Again, this is that correlations plot. And your regression coefficients. This shows you how much each variable contributes to that factor. So factor 2 is high for fair leader, inspiration, enjoyment. It's not very affected by your security or your creativity, and it's anti-correlated with your conflicting feedback, too high expectations, and so on. You can look at your significant effects. So this too high expectations, it crosses 0 here. So that means that it's not really a predicting variable because it can go both positive and negative along with the job satisfaction. So you probably don't want to use those variables. It's just a way of selecting the variables that are the most important to predict, in this case, job satisfaction. Oh, I already did the octane example. So again, you want to look at your outliers in your regression. Your X outliers you can see in your scores. And often you might want to do a principal components analysis before you do your PLS to see if there's anything grossly standing out, like those additives in the octane. On the XY relation outliers, a sample may look okay in both individually, the X and the Y space, but when you plot them against each other, the relationship may disagree in structure, kind of like we showed with the temperature and pH earlier. So we have automatic distance measurements, so you can look at your residual variance, leverage, Hotelling t-squared limit. I will show you that in your octane. So your residuals and influence here. This is your Hotelling t-squares. That basically tells you how far from the center of the model each data point is. And you can change this line of significance to be more or less strict depending on your needs. And this is your influence, so this has your Hotelling t-squared, and you're looking at your residuals. The key residuals here looks at how well the calibration is predicting. So if you have high Q residuals, when you reconstruct the original spectra, this is how much is left over, like how different the reconstructed data is from the original data. If you find anything that is in this space that has both a high Hotelling t-squared and a high Q residuals, that's a very good indication that you have an outlier. If you have a high Hotelling t-square, that's an extreme sample, maybe an interesting sample, and you have to decide whether you want to leave it in your data or not. We can see that here in the other one where we did not include it. So here you see one of our data points that has the additive is very far from the center of the model, and one actually doesn't reconstruct very well. So those are two different types of potential outliers that you have. And these are just all your graphical tools that you can look at to discover whether you have outliers or not. So when you use your PLSR model for prediction, in your calibration stage, that's where you define your outliers, you refine until you get your model to where you want it, you choose your variables, and you do a cross-validation. And then you also, the best thing to do is also have a test set validation. So you have your X plus your Y, and that gives you your model. The second step then is you do your prediction. So you have your prediction, so you have new data, new X data that you don't know what the Y is. You put that into your model and you predict what your Y is. Prediction is straightforward once the model is built. In the unscrambler, it automatically applies any pretreatments that you do to your data. Let's say you do a derivative or a normalization. It will automatically do that to the new data coming in, and it will apply the same number of components that you determine. You still have to look at your outlier detection, especially when you're predicting unknown samples. So keep an eye out for that. So outliers, you have different types of outliers. Again, you have something that is in the same plane. They are similar. This is your Hotelling t-squared score. So it has a high leverage, meaning that it's in the plane of the space of the model, but it's an extreme sample and it's pulling the model to it. And samples with a high residual means that it's not explained very well. It's outside of the space of the model. And this is just a different way you can look at your uncertainty limits at prediction. If they're similar to your calibration objects and have small uncertainties, that means that it's a reliable prediction. If they're dissimilar, you will see a high uncertainty, and then it's an unreliable prediction. So in your modeling phase, make sure that you think about your project before you go in. Prepare a workflow, know what your objective is, Don't look for correlations in the raw data by plotting endless columns of data. And don't mix significance and relevance or prediction ability. With lots of large samples, everything is found significant. You can fit any model to 100%, but the way that you prove that your model is good is by validation. And there's nothing wrong with concluding that in a specific case there is no valid model. There's different levels for valid models. In consumer science, you might be fine with 4 to 50% because people are very variable. If you are doing process modeling, 65% might be well, like when we looked at the paper. And in analytical chemistry, you're looking at 90 to 99%, so it really depends on your particular data. And again, I'm going to instill this in you, is always make sure you validate your model. Confirm that it makes sense to your hypothesis, internal validation with your cross-validation and test set, and then you need to, models are fluid things. They're not make a model and leave it. You might get new extreme samples that you didn't incorporate at the beginning, so you need to keep an eye out for outliers and decide if you need to update your model if there's new data. It's just different ways you can collect data. I'm going to skip through this for now. You collect your data, check the data. Make a model, check the model. Apply the model on new samples, and then you get your results. So these are just some of the steps you go through. I'm running out of time, so this is just a little rehashing. So I'm going to open up for questions now. I have one question of how do you choose if you need to use PLS or PCA modeling? So basically, they give you different information. In a PCA modeling, you're looking at qualitative data. So that's usually if you want to look at different groupings, if you want to see patterns in your data, but you're not trying to predict an outcome necessarily. You might want to predict that something's in a group, different types of groups, where PLS gives you a quantitative value. I've got, which pre-processing method do you recommend for PLS in NIR spectroscopy? That's going to depend on your particular data set, actually. So I'm going to do another webinar later in the year that's going to look at PLS and PCA for NIR spectroscopy specifically, so we can go through some of that then as well. The minimal number of samples required to create a model. I would say in general, you want at least 30 data points to make a reasonable model. That's a rule of thumb in statistics, but more is better. It depends on how complicated your data is. Oh, people are asking if the presentation will be made available. Yes, I did record the webinar, and we will have that on our website, and we will send you a link to that. What is the best way of determining accuracy using RPD? Is it standard deviation of reference or RMSE? So I usually use the RMSEC and RMSEP. Your error of calibration tells you your internal accuracy, but really when you validate, it's best to have an external test set. So that would be your RMSE EP. Okay, can you explain again the factor reduction in the paper example? Yes. I'll go through that real quickly. Task analyze. To remember to weight my data. Here is where I have this uncertainty test. That's the one that helps me figure this out. Oh, how does it handle missing data? Oh, I forgot to choose the right ones. Process quality, training. So I have to get back to you that on how it handles missing data. Oh, I do have a question. What is the maximum number of variables you can use in a model? Because proteomic data have hundreds of proteins per sample, and you want to determine significant proteins. So it depends on how complicated your data is. I start to get a little nervous if you're using more than 4 or 5 components, but in something like proteins or agricultural samples, you might see 15, 10 to 15. You don't want to get to the point where you're taking 40. So it really depends on how complicated your data is. So here's where we looked at the variable selection. Using that uncertainty test, it automatically chose what it thinks are the most important variables. You can choose them yourself as well. You can unmark them all. In this case, I might look at these correlation loadings and mark only the ones that are outside of this 50% line. So we'll include that. And that tells you those are the ones that you want to keep in. And you right-click and you can recalculate with your unmarked down-weighted. That way that the variables that you left out are still, they're multiplied by a very tiny number, so they're still in your area. So now this is interesting. We see that the prediction went really bad. So one of those variables that I took out was actually important for prediction. But if we go back, we can unmark all. And this here is your mark significant X variables again. That will mark all of the ones that you want. Recalculate with unmarked downweighted. And that's how we do that. I have a question about using a design of experiments, which is not really going to be covered in this webinar, but I'm hoping to have a webinar on that later, or I can talk to you offline about that. I believe that's all the questions that we have for now. I want to thank everyone again for coming, and I appreciate your feedback, and I hope you all have a great day. We will have our next webinar is going to be in April, and it's going to be looking at sensory data.